Okay, so in the last lecture we had seen that a sequential digital system can be modeled in the form of a block diagram shown over here, where we model a system in terms of a number of states, and the system goes from one state to the next in response to the inputs, and the outputs also depend on the states as well as the applied input here. So this is the block diagram by which we try to model the sequential digital system. And in order to design this block diagram, we start from the state transition graph. So whatever is the problem that we are trying to design, the first thing that we need to do is from the description of the problem, we try to model it as a state transition graph. So the steps involved are we try to identify what the states of the systems are, S0, S1, S2, S3, and how the system goes from one state to the next in response to the inputs, and what the outputs are. So once we model the problem in the form of state transition graph, then we can go ahead and synthesize these three blocks that you see here: state memory, output logic, and next state logic. And we had seen that we require the following steps. The first step is state minimization. So when we capture the problem in the form of a state transition graph, it may be that we have used more states than are really necessary. In other words, that there may be redundant states. So what we need to do is relook at the state transition graph and see if there are some extra states or states that are not really required present in a state transition graph. The reason why we want to do state minimization is that we want to use as less state memory as possible, because that would result in more area efficient design here. So once we get a reduced state transition graph, then we go through a process called state encoding. So we assign a bit pattern to these states here, S0, S1, S2, S3. And once we have a bit pattern, then what we need to do is, after these two things, we need to choose a flip-flop type to implement the states here. So whether it's a JK flip-flop or a D flip-flop. And once we are done with these three steps, then basically we have implemented the state memory. The state memory in the form of D flip-flops or JK flip-flops, we have implemented that. And so the outputs of the flip-flops will be the present state of the system here. The inputs to the flip-flops are what determines the next state here. So we know now what is the truth table of the next state logic. And from the state transition graph, we know that for the present state and for a given input, what the required output is supposed to be. And therefore, we know the truth table of the output logic. So we can synthesize the next state logic and we can synthesize the output logic here. So let's look at the problem that we were discussing. So we had these state transition graph with 4 states. And we know that one of the states is redundant, but we, for the time being, will not bother with it. So assuming that this is the reduced state transition graph, what we need to do then is assign bit pattern to each one of these states. And we had seen earlier that we can use binary coding, or we could use gray code or one hot code. In this case, let's stick with binary coding, which means we'll use 4 states are there. So we'll use 2 bits to encode these states. And so this is an arbitrary encoding scheme here. S0, 01, S1, 10, S2, 11, and S3, 00. There are many different ways of encoding. We could have taken S0 as 00, S1 as 01, and so on and so forth. And we'll see shortly what the consequences of choosing different codes are. Now, so once we have assigned these bit pattern to these codes, in the present example, we have decided to implement the state memory in the form of a D flip-flop here. So since there are, we've chosen 2 flip-flops, 2 bits, so 2 flip-flops. And so these are, the outputs are Q0, Q1, they denote the present state of the system here. The inputs, as we have said, denote the next state of the system here. So this is a state memory. And from the problem and from the bit pattern that we have assigned, we can now write down this truth table here. So from the what we need to do is, as we can see, to synthesize the next state logic, we need the values of D0 and D1. So those are the output values of the next state logic here, which are written here, D1 and D0. And we also need to determine Z. So this is Z here. And how do we determine these values here? Well, D1 and D0 we determine depending on what transitions are required. So from S0 to S1 or S1 to S2 and all that. So that's what we do in this particular table here. So this is the present state. Let's say the present state is S0, which is 0, 1. And when an input 0 comes, we can see here it stays in the same state. So the next state is 0, 1. So the present state is 0, 1, Q1, Q0 is 0, 1. The next state is 0, 1 here. And therefore, the D1 and D0 values that are required are simply 0, 1. So whatever is the next state that is required, 0, 1, the same value of D1 and D0 are required at the inputs here. So next is, if the present state is 0, 1 and we get a 1, then the next state is 1, 0. From the state transition graph, we can see it goes to state S1, which is 1, 0 here. So from 0, 1, we go to 1, 0 here. The output is 0, and 1, 0 implies that we need inputs, the flip-flop inputs as 1 and 0 here. So similarly, next we take state 1, 0, S1, and we look at it when we get a 0 or when we get a 1. Then we look at the state S2, which is 1, 1, when we get a 0, when we get a 1. And similarly, we look at the last state, 0, 0, and when we get an input as 0 or input as 1 here. And we write down what the next states are and what the output values are and what the required D1, D0s are. So once we have that, then we can determine what is the expression for D0 and D1. And let's do that. So we can, suppose we want to determine D1. Then D1, you can see here, we express D1 in terms of the present state, Q1, Q0, and X here. So we take a K-map and we fill up this truth table here. And we minimize and we get an expression for D1. And similarly, we look at D0. And D0, again, we would like to express, note that D0 is determined by the present state and the X value here. So again, we use this truth table here. And we fill up the K-map and we minimize it, we get an expression for D0. And lastly, we find an expression, Boolean expression for Z here, which is X, Q1, Q0 here. So note that these expressions that we have found, D0, D1, and Z here, so D0 and D1 are here, these two expressions. So once we implement these expressions in the form of a gate netlist, they will form the next state logic here. So I'm not going to go into the gate implementation here, straightforward to implement these two here. Similarly, we can take this and implement it in the form of gates, so we'll get the output logic here. So that would complete our design of the final state machine. Now note that we had said that we had assigned one particular set of codes to S0, S1, and S2. S2 and S3. So in this particular case, we have assigned a different code here. S0, 00, 01, 10, and 11. And we have gone through the synthesis process. So again, we filled up the state transition table here to determine D1, D0, and Z here. And so the same process we repeat. We get D0 equal to X after minimization. D1 is X bar Q0. And Z is X Q1 Q0 bar here. So we get all these different expressions. And from these expressions, again, we can fill up the next state logic and we can fill up the output logic here. So let's compare the two coding schemes here. This was the first coding scheme and these were the minimized expressions that we get here. Now, in order to assess the complexity of the next state logic, which is D1 and D0, or the output logic, what we need to do is, as we said, implement them in the form of gates and then look at the area of all the gates here and add them up and determine what the total area cost is for this particular implementation. Now, in this particular case, we'll do a quick estimate. Each logical operation that you see here, so there is an operation, AND operation between X and Q1, and there's another AND operation between Q1 and Q0. So each operation will count as a gate. In other words, this one that you see here, we'll implement it as in the form of two input gates here. So Q1, Q0, one AND gate, and then the output here is ANDed with another AND gate here. So we'll say that the cost of implementation of this particular output logic is 2 gates here. Note that there are other ways of implementing. We could have used a 3-input AND gate as well, and there are many other ways. So right now, what we want to do is just compare the two codes. So we have a very simple estimate of how many 2-input gates will be required to implement Z. So in this case, the cost is 2. In this case, if we look at it here, this is a 3-input here. So this part we implement here. and x cube 0 we implement here, q1 q0 we implement here, and then there are these OR gates that are required here, OR gate and OR gate required here. So we are implementing again in the using only 2 input and an OR gates. So we can see here the cost of implementing this is 1, 2, 3, 4, 5, 6. So 6 2 input gates here, which is also the same as counting how many operations we have to do here. So there is one AND here, 1 or 2, and here 3 or 4, and here 5, and here 6 here. So 6 operations are required to compute D1. We are not counting the complements here, assuming that Q0 complement and Q1 complement are available, and we are not counting the additional gates that may be required here. So the cost of implementing both the output logic as well as the next state logic is going to be 2 plus 6 plus 2 here, which is 10. Let's look at the other state encoding scheme. So this one is the other scheme for which we had obtained these minimized expressions, Z, D1 and D0. So we add them up, we get a cost of 2 here, and in this case we get a cost of 1, 2, 3 and 4 here. There's no cost in implementing D0, it's simply equal to input. So the total cost is 6 here. So rather than the actual numbers, what is interesting is that 2 different ways of encoding, same number of bits have been used, but 2 different ways of encoding the states produces 2 different results here in terms of how much is the complexity of the output and next state logic in the 2 cases here. So in this case happens to be, it appears that it will take more area as compared to this one. All right, so what we would like to do is determine what is the best way of assigning. If different ways of assigning codes produce different results, then what we would like to know is what is the best way of assigning codes to these states here. Now, unfortunately, there is no well-defined mathematical principle that we can follow to assign these particular values here. What we can do is, what people have come up is a set of rules of thumb, also called heuristics. If you follow those heuristics, it's likely that the result that you will get will be efficient. It doesn't guarantee that in every particular case the implementation would be the best possible implementation, but generally those rules of thumb produce good results here. And the heuristics that I'm talking about are based on the concept of distance between 2 codes here. So if I have a code 101 and another one 010, then the distance between these 2 codes is 3. Now, distance in the sense how many bits I need to flip in order to arrive at this particular code. So I need to flip this one, I need to flip this one, and I need to flip this one. So 3 bits I need to flip in order to arrive at this particular code. So the distance between them is 3. In this case, I don't need to flip. I need to flip this one. I don't need to flip this. So I need to flip only 1 bit. So the distance between the 2 codes is equal to 1 here. So the heuristics that I'm describing are based on the distance between the codes here. So the some heuristics are summarized here. So what it says is that one should look for patterns such as the ones 3 patterns that are shown here. Let's look at case 1. Case 1 says that if you see a state alpha and you see a state beta, and for a given input I, both inputs are I to beta as well, and input is I to alpha itself, and if both of them go to the same state, then what you should do is try to assign a code to alpha and to beta such that the distance between them is minimum. Right? So this is what this particular heuristic is saying. If you see a pattern like this, then assign code to alpha and code to beta such that the distance between them is minimum. The next case is if you see a state which branches into 2 states like this, alpha and beta. Doesn't matter what the input output transitions are, but if from one state you see a branch to a state alpha and a state beta, then what it says is assign codes to alpha and beta such that the distance between them is minimum. Then in the next case it says if you see a state alpha and which goes to some state but for the same input output transitions, and similarly a state beta which goes to some state but for the same input output transitions, then try to assign codes to alpha and beta which are as close as possible here. Now the heuristics also say that this case 1 has the highest priority. So first you should make sure that these cases the codes have the minimum distance. Then after you've exhausted such cases, then you should go to case 2 and then assign these particular states codes which are as near as possible here. After you've exhausted case 2, then you should go to case 3. So use these heuristics and assign codes, and the chances are, the likelihood is that the design that you'll produce is more efficient than some random way of assigning codes here. Alright, so let's see the example that we were looking at. S0, S1, S2, S3, this was the state transition graph. These are the heuristics that we would like to follow. So let's look at, we can identify case 1. Let's look for case 1. Case 1 is when two states alpha and beta, they go to the same state here. So we examine the state transition graph. We can see S1 and S3. Both S1 and S3 go to state S2 when we get a 0 here. And 0 here and 0 here both go to that. So we can identify case 1. There are no other patterns in this particular state transition graph which obey this particular rule. Let's look at case 2. State S2 goes to S0, S3. We can see here S2 goes to S0 and S2 goes to S3 here. So we see this here. Case S3 goes to S1 here, goes to S2 here. So this is there. So case 2 is there. And then similarly we can identify case 3 as well. So let's assign the bit pattern now. So we've identified these different cases that are there. This is the highest priority. So the first thing we do is assign S1 and S3 codes which are as near as possible here. So we can do that 0, 0 and 0, 1. Well, fine. So we have S1 which is 0, 1. The next thing is we can look at these, assign S1 is 0, 0. So we assign S2 which is as close as possible, 1, 0 here. And S3 we've already assigned 0, 1. So we try to assign S0 which is as close as possible, which is 1, 1. And when we come here, S3 and S2, we can't do much. We've already assigned S3, 0, 1, S2, 1, 0. This is the least priority. And we find the distance between these two codes is 2 here. So this is one way of assigning codes. And starting with the highest priority here, then this one, and then this particular one. Okay, so this is the encoding scheme that we find here. S0 is 1, 1, S1 is 0, 0, S2 is 1, 0, S3 is 0, 1 here. All right. So, we've looked at then the synthesis of a final stage machine, and we said earlier that there are two possibilities in terms of modeling a final state machine. One is a Mealy sequential machine, and the other one is a more FSM here. And we had also said that both of them are very general in nature. Mealy FSM can be converted into more, and more can be converted into Mealy here. So this is the Mealy sequential system here. This is the more sequential system here. And one can see the differences between them. This is the Mealy sequential system, FSM, and this is the more sequential system here. If we note that differences are that the output here depends not only on the present state, but it depends on the X itself here. While in the more sequential system, the output Z does not directly depend on X. It depends only on the present state here. X, of course, affects Z, but only after going through into the state memory. Then only it affects Z here. So this is the basic difference between the two. Z, direct dependence of Z on X, and no direct dependence of Z on X here. And because of this direct dependence of Z on X as well as present state here, the Mealy machines are in general more efficient in the sense that you can implement them with lesser number of states as compared to a more sequential system here. Now, in this particular example, here there are 4 states and here there are 3 states. If we try to minimize the state memory, we'll still require 2 bits to implement this, and we'll still require 2 bits to implement this. So there doesn't seem to be too much of a saving. But imagine if a case where this one were 5 states and this one were 4 states. So if we try to use minimal state memory, 5 states would have required 3 flip-flop at least, and 4 states we would have used only 2 flip-flops, and therefore we could have saved one flip-flop in implementing the state memory here. So what we are trying to say is that Mealy machines in general use less number of states as more, and therefore the amount of memory that you need may be a little less in case of Mealy. The other one is Mealy machines can react faster. If an input X changes here, the output immediately responds to X. While in this case, if X changes here, then X has to go and modify the state memory and then affect the output here. So in some sense, Mealy machines can be faster, but then that can be a problem with this particular system here also, in the sense that if there is some unwanted transition in X, for example, there could be a glitch in X, in the sense that normally, let's say the value of X is 1, but very briefly it goes to 0. Some unwanted transition to 0 here. So there's a glitch. Now, in this case, the glitch will propagate to the output here. While in this case, if there is a glitch here, the glitch is not going to affect because it's not going to go into the state memory. What goes into the state memory only goes once the clock comes. So a brief glitch in X is unlikely to modify the state memory, and therefore the output Z will not be affected. While in this case, any glitch in X propagates to Z here. All right, so these are the some basic differences between the Mealy sequential machine and Moore machine. And as we said, you can model the sequential system in a very general way, either with this particular approach or in this particular approach. Note again, in this case, the outputs are dependent only on the state. So that's why they're written inside the state here. So 0 refers to that the output is 0 for state S0, 0 for state S1, 0 for state S2, and 1 for S3. While in this case, the outputs depend not only on the present state, but also depend on the input that has come. So when you go from S0 to S1, so the output is 0 here. So output depends on the state as well as the input, and that's why it's written next to the arrow here, which lists the input values here. All right, so suppose we have synthesized the finite state machine. This is an example of finite state machine, and what we would like to know is what is the clock rate for this particular machine. In general, I may want to run the clock as fast as possible in order to get a faster system, and so we would like to determine the highest clock rate. Now, the highest clock rate depends on, as may be obvious, will depend on the delays associated with these particular gates, and also delays associated with the flip-flop here. So let's look at the delays associated with the flip-flop first. So this is an example of a D flip-flop, and these are the delay values that are listed for a D flip-flop for 180 nanometer CMOS technology here. And there are different kinds of D flip-flops of different strengths. So we'll concentrate on a flip-flop with 1x strength here. This is a flip-flop with higher strength. So this particular flip-flop, if we look at it, there are several delay values that are written. So this is the delay value from clock to Q. So once a clock, this is a positive edge trigger system. So once a clock comes here, so what we are asking is after how much time does the Q respond here. So this is clock to Q when Q goes up. This is clock to Q when Q is making a 1 to 0 transition here. So these are the delay values here. And this is for the complement part here, Q complement here. So the worst case value for this particular delay is 0.280 nanosecond. But note also that what is written here is intrinsic delay. So this is the intrinsic delay, means that this is delay of the flip-flop when nothing is connected to the outputs here. But that's not a practical case. What we are likely to find is a flip-flop which is connected to some gate. The outputs are connected to some gate. In our case, what we'll do is we'll take a NAND gate as a load for a flip-flop. Now, what happens is when you connect a gate here, it adds capacitance to that particular output node. And now when the flip-flop is making a transition, low to high or high to low, those capacitors have to be charged. So there's an additional delay which comes about because of what you connect to the output node here. And so this describes the additional delay that comes in. It says that for every PF of load capacitance, the delay increases by 2.444 nanosecond here. So what it means is that the net delay from clock to Q will be intrinsic delay plus the 2.44 multiplied by whatever is the load capacitance here. So the net delay is 0.28 plus 2.44 multiplied by the input capacitance of the NAND gate here, which for this 180 nanometer is 0.004 picosecond, 0.004 picofarad here. So 4 femtofarad. So we add them up together, we get a net delay from clock to QN of 0.29 nanosecond here. Note that the second part the loading is not too much when I have a single NAND gate, but I could have connected 2 NAND gates here, so this factor would become double, or I could connect 4 NAND gates here, so it would become 4 times as much, and then the contribution of the load capacitance may become significant here. So that's one of the delays, clock to Q delay. There are other delays. One of them is the setup delay, and the other one is the hold delay. So let's look at the setup delay. So setup delay can be understood from this particular diagram here. So what it says is the following. This is the clock, positive edge triggered clock. So setup delay, what it says is that the input, whatever input you want to be latched to be transmitted to the output, the input should become stable, which means that it should not change for a time equal to the setup time measured from the clock edge here. Okay, so from 50% point here to 50% point here. So what it says is the input should be stable. You should not change the input after this particular point. Okay, before the clock edge, the input should be stable. If it's supposed to be 0, it should be 0 and should not change afterwards here. If it's supposed to be 1, it should be stable and 1 and should not change. So that's the setup delay here. And for our system, the setup delay is 0.15 nanosecond. If we go back here, it says setup when input is going from 0 to 1 is 0.06. When input is going 1 to 0 is 0.15. So we'll take the worst case value, which is 0.15 nanosecond here. Then the next thing is the hold delay. So the hold delay says that you not only have to keep the data stable before the clock edge comes for a time called the setup time, but you need to keep the data stable for a certain time after the clock edge here. And so this particular time is denoted as the hold time. And if the input was supposed to be 0, you should keep it 0 till the hold time. After that, the input can change. It will not affect the output here. But within this particular time, if you change the input, then the proper value may not get transmitted to the flip-flop outputs here. So hold delay for us in this case is not significant. It's actually negative, which means that there's no need to keep the input stable after the clock edge here. Okay. All right. So with these definitions, let's try and determine the maximum rate at which we can run the clock here. So note that so what happens is once the clock. So let's look at it. This is the next state logic. Next state logic, it produces the D values here, which get latched on the next clock cycle here. This is the memory here, and this is the output logic here. So let's look at the clock and decide what is the minimum time period that we can use, and still the system works properly here. So note that what happens is once the clock edge comes, once the clock edge is here, let's say, then what happens is then whatever was the value D here, it propagates to the output, and we have a delay called clock to Q delay here. So from clock to Q delay, so the A is now available at this particular point here. Now this A, we can see here, of course, goes here and produces the output, but what we are interested in, this A is also goes back here. This A goes here, and then it goes through a delay here, and then a delay here, and then is available here. So the value which we want to be latched at this particular clock edge now becomes available at this particular point here, after going through a delay through this combinational logic here. So this is the delay through the combinational logic. Delay through basically the next state logic here, combinational logic. And so whatever is the value that you want to be latched now, it's available here, and this should be available at least a setup time before the clock edge here. So this is setup time here. At least a setup time before the clock edge here. So what we are finding is that the time period for the clock should be greater than the clock to Q delay here, plus the combinational logic delay here, plus the setup time here. Must be greater than this. If we try to make the clock shorter than this particular one, then what will end up is violating the setup time, which means that the data would still be changing for a time duration which is less than the setup time before the clock edge, and therefore the proper values will not get lashed into my flip-flop here. So for our example, clock to Q delay was 0.29. The AND gate and the OR gate delay, they add up to 0.29, and the setup time was 0.15, so they add up to 0.73 nanosecond, and therefore the clock frequency is less than 1.37 gigahertz here. So this is the maximum clock rate that we can use for this particular system. Of course, to be on the safe side, we'll have to keep some margin. Even though we've used the worst case delay values, the delay values may still change. For example, if the temperature of the IC goes high, the delay values may further increase, and therefore the system may not run at that particular clock frequency here. So anyway, we should try and take the worst case values here and maybe and then determine from there here.